Welcome back. I could not leave you hanging there on our first day using the fundamental theorem of calculus before we actually put it to practice. So I'd like you to turn in your definite integrals packet to the examples that are on page 6 so we can see the fundamental theorem in action. Let's do some work first. We want to evaluate this integral from 0 to 2 in number 1. Circle this one. It's a good question. Antiderivative. So 2x's integral is going to be x squared, right? It'll be over 2 and then times 2 with those canceling, minus the integral of 3, so minus 3x, evaluated from 0 to 2. And my new fundamental theorem says plug in a 2, subtract what you get when you plug in a 0. So here goes, 2 squared minus 3 times 2, minus, now let's plug in 0, 0 squared minus 3 times 0. So like happens some other times, this will give you something, 4 minus 6. That won't give you much. Minus 0 gives us an answer of negative 2. And that is the answer for the definite integral in this situation. I question this for a second because the past couple of days we've been trying to relate a definite integral to the notion of area under a curve. Have we talked about negative area values? I just want to make sure that this is making sense. Let's look at the picture to confirm this for ourselves. Can you plot a sketch of 2x minus 3? So it's a line that's shifted down 3 units, and the slope of it is 2. You're over 1 up 2 a couple times to get this line. I've sort of missed the points there, but that's the idea. You want to find the integral from, what was it, 0 to 2? So I actually want to shade this area to see if an answer like negative 2 makes some sense. So to go from here to there, the area between the curve, the line, and the x-axis is 2 separate chunks. It's this shaded area down here, and it's this little triangle that's shaded above. A negative area for units squared does make some sense here because negative area is area below the x-axis. So that whole part of the area counts as negative, and this whole part of the area counts as positive. So you do get a negative value, and in this picture, it should make some sense. Let's try the second one. Let's see if we can start from the beginning here. We want to take an antiderivative of x to the third plus 2x. So go ahead and integrate. Give it a try. So x to the fourth over 4 plus, well, 2x, we had that in the last one. Its integral should just be x squared, evaluated from negative 1 up till 1. What are we going to get? Let's plug in. So 1 to the fourth over 4 plus 1 minus, let me be more careful with parentheses, negative 1 to the fourth over 4 plus negative 1 squared. And that was squared, but that is just a 1. All right, let me move myself out of the way a little bit here. And you get 1/4 plus 1 minus the same thing, right? 1/4 plus 1, so minus positive 1/4, because that negative is raised to an even power, plus 1. You get something minus itself. The answer for this is 0 or 0 square units. Can that be an area? Do we agree with that? Well, absolutely. If I were to sketch this one, I get an S-curve. And because of how symmetric we made the interval, we were going from negative 1 to 1. Turns out that the negative area below the curve is going to cancel out with all the positive that we had above. So this cancels that negative, cancels out with the positive. You get an answer of 0 square units. No need to question. I want to skip down, just look at one more, and one of the ones that's got x or t in it. Let's try the t one. Let's try number 5 just to make sure we're on the same page. And it's an definite integral from 1 to 4 of t minus 3 over t. Don't forget all of your integration rules that you used before this, right? We don't want to integrate this as a quotient if we can avoid that. We want to either divide both parts by t or swing a t up and make it to the negative 1. I think most often we've been rewriting it this way, just so that it's not a quotient anymore. And we'll put a dt after that. So you want to take the definite integral from 1 to 4. Let's add these powers. So of t to the 0 minus 3t to the negative 1. This will be a good one. Let's rewrite. I know anything to the 0 power is 1. So it's the integral from 1 to 4 of 1 minus, this can be 3 over t, taken with respect to t. And let me see what integral rules you remember. Now it's time to take an antiderivative. So integral of 1 would just be x, or t in this case, because that's the variable we're using. The 3 stays in the next part because a constant always stays in your antiderivative, but a 1 over t has a special rule, right? What function has a derivative of 1 over t? That would be natural log. ln of absolute value of t. Usually there'd be a plus c, but instead we're just going to evaluate this from 1 to 4. That'll be our plug-in. So go ahead, plug in 4 first. Make it 4 minus 3 ln of 4 minus 1 minus 3 ln of 1. Like that. I think I left this answer, I ended up leaving this answer as a decimal. A couple of the things do cancel out, but you'll have, I think, rounded to the nearest thousandth, it'll be negative 1.159. I sketched a graph of this to confirm that it looks good to get a negative area here. You end up with a hyperbola that's got branches in quadrants 3 and then over in 1 and 4 like this. It was a little bit easier to see that this answer made sense when I looked at Desmos, so I just graphed it in terms of x minus 3 over x. And then notice over here, if you're going from 1 to 4, you have a tiny chunk of area above the curve and a greater space below the curve, meaning a negative answer here would be good too. All right. Hope you've been enjoying yourself so far this week. Keep up all the good work, and I'll see you next time.